What about now? What about now? All right, live. Hey, how's it going? Happy day. 28th of April, 28th day of the 30-day challenge. Looks like we've got another problem. It doesn't actually sound that awful though. So in this one, you have a queue of integers and you need to retrieve the first unique integer in the queue, which sounds awful lot like one of the first problems we did. Single number. So you have a queue of integers, you need to retrieve the first unique. So in single number, you had to find the unique value in an array. But in this case, we need to return the first one, so that's kind of messy. So we need to keep track as we go along, and that's okay. This also reminds me of the LRU one that we did earlier this week, where we had to basically kind of keep track of items as we went along, and it also kind of gave us an API interface that we had to meet, so we had to do the get and the puts. So all that is sounding familiar. So I'm probably missing something. You have a queue of integers, you need to return the first unique. Implement the FirstUnique class that gives an interface. We have a constructor, a showFirstUnique, which returns the value of the first one, or -1. And then we add. So we don't have to worry about removing. That's interesting. On the example below, they give us an array of 2, 3, 5. Each one is unique. So they say show first, we return 2, they add a 5, now we got 2, 3, 5, 5. 2 is still the first unique though. And if they add a 2, then the next unique is now 3. All right. And okay, so that doesn't sound too bad. I'm kind of thinking that I want to have a hash table for quick lookups so that I can know whenever I add an item. Do I want a hash table? What I was kind of thinking is basically having a hash table that would kind of keep track of the items that are already in there. You know, they tell you it's a queue of integers, but do you really have to keep the items after you find out there's more than one, or can you just toss them and just keep track of the fact that you have ever seen more than one of them? Well, it's kind of interesting. So in the first example, they give us a 2, 3, 5. We put it in our hash table with a count of 1. We have to keep a sorted hash table though, which hash tables don't guarantee ordering, so we'd have to make that happen by having a secondary data structure that keeps track of the order. And then whenever they say, hey, show first unique, we would return the first item that has a 1 value in the hash table. So we basically need a sorted hash table. And then we can delete items from we only need to keep the items around that have 1, or else we have to be able to tell that we've at least seen them more than once. So I guess we do have to keep them around in some capacity. So we definitely don't have to keep this big list of items like this, because there's no way to remove items. Only add. Okay. Oh, we have hints. Ooh, that's a big number. 10 to the 5. 100,000. The numbers aren't that big. No, wait, 10 to the 8. Okay, yeah, that's what? 100 million? Something like that. And same with the value. Okay, so that's pretty big. And at most 50,000 calls. That's pretty big. That's a lot of numbers. So we do have hints though. Use doubly linked list. Oh, my arch nemesis from the LRU problem. Use doubly linked list with a hash map of pointers. This is exactly like we did with the LRU. Linked list with a hash map of pointers to the nodes. Add unique number to the linked list. When add is called, check if the added number is unique, then have it added to the linked list. And if it is repeated, remove it from the linked list if it exists. When showFirstUnique is called, retrieve the head of the linked list. I mean, that sounds like the exact solution to me. Use queue and check that the first element of the queue is always unique. Otherwise, we can remove it, sure. Use set or a heap to make running time of each function of log n. Okay, I mean, we also programmed a heap the other day, so this doesn't really sound like much of a problem. It just sounds like it's more about kind of like traditional programming than it is like figuring out the clever algorithm. So where does the heap come in, or the set? That would be, heap is good at keeping either like the minimum value or the maximum value. Huh. So how does that help us? The thing that's nice about a heap is that it's easy to pluck items off of it. So if we had to remove an item because it's no longer unique, well, we would only ever... Okay, so it's kind of fast to pluck stuff off, but then after you remove the top item, you have to decide which the next one is. So you presumably look at the value and say, okay, this one was added second or third or something. I don't know, it's kind of weird. Maybe that will become more apparent if we start why you would want to do that, but so far it doesn't really seem that exciting to me. All right, well, hash map that's basically built in to JavaScript, so no need there. Lesson I learned from the LRU problem is that I'm going to separate my data structure from my solution and test it independently so I don't get bogged down trying to kind of debug that as part of the greater solution. So let's do this. I only need one linked list. So I could do something like... I think the way that LeetCode runs the solution is it ends up kind of like running the same code over and over again, maybe. So I got to be careful with globals. So I will make this a function. Something like this. And it will return a new doubly linked list. We don't have to keep track of the last item. So it's enough just to say we've got a linked list. This is the head of it, so it will never be completely empty. We have to remember that having one item in there is essentially the same. So that's good. What else? Linked list needs to be able to add items. Items will always go on to the end. Yes. So in that case, it does benefit us to know the last item. So maybe I could just do something like a head and tail here. Okay. Let's see. What if I just returned a new object like this? I'm sure there's a better way to do this in JavaScript. And by the way, if you know of a better way to do this in JavaScript, let me know. So I don't really do object-y type stuff in JS most of the time. And I will go ahead and do this in code because we're going to end up there eventually anyway. It makes it easier to write individual test functions to test smaller parts. So what do we call this? Unique. All right, 2 days left of the contest. I'm very excited. So we need a function called add, which will take a value. And what it'll do is it'll take list.tail, which is the last item in the list, and set its next value equal to a new node with a value of my value. Its next will be null, and its previous will be list.tail. Of course, this assumes that we actually have a list tail, so that's going to be a little bit different. Oh, and before I do that, actually, list.tail next equals blah blah. So I also need to set here. Let's just do it like this. New node equals, we create the new node. It has no list because it's going to be the last item, and it does have a previous set to the current last item in the list. Then list.tail, its next value needs to become new node, and then finally list.tail becomes new node. There's something that makes me uncomfortable about kind of phrasing it this way, so I'm just going to say your previous, which we just set. It's the same thing, it just, I don't know, reads better to me. We're going to say your previous is next equals new node. And that should do it. But like I kind of alluded to earlier, this only handles the case where we already have a value. And we have a special case here where if list.tail is already null, like this is the first item ever, then what? So a little bit different. So in this case, we have to set the list.head equal to our new node. New node doesn't have a previous, so we can leave that as null. So just for clarity's sake, I'm going to kind of leave it unattached, and we'll just assemble this thing all in one spot. I just think that reads better. And like I ran into with the LRU, I got bogged down debugging. Hey, how's it going, Trent? Do I need to check if the list is null? That way you don't set the previous? Yes, for sure. So what we'll do here is basically, if we don't have a tail element, which is kind of the same thing as saying our list is empty, then we're going to set our head value to the new node, and our tail to our new node. It has no next, it has no previous, and so good catch, that's totally what we need to do. Now if we do have items in the list, then new node's previous, so now I'm not setting the previous, so its previous is going to be equal to list.tail, so that's the last item in the current list. Its next is going to stay null, so we don't have to worry about that. But we do have to go to its previous and set its next equal to our new node. So now the item that was previously last knows about this new one. And then finally we have to set list tail equal to our new node, which is common to both of these cases. So we'll leave it like that. How's that look, Trent? So we do have to remove, but in this special case, I think we're only ever going to remove the head. Awesome, glad to hear it, thank you. I tend to make lots of mistakes, especially when I'm gabbing. So list.remove head. This function takes no arguments, and what it'll do is I think I can assume that we will always have a head if we're calling this. But just in case, if the list dot head equals null, or what? Or nothing. Return. And if there's any other case, then what? Oh, there's one other special case. If the list.head equals list.tail, so there's only one item in the list, then list.head equals null and list.next, no, sorry, tail equals null. That will remove our node. Okay. Yeah, that's good. And we don't have to worry. I was trying to think if there's like a memory leak here, because the node I'm removing could potentially have its next or previous value set, so it would kind of like contain a pointer to another object that would prevent it from being cleaned up until that other object gets cleaned up. But I don't have to worry about that for this condition here. And we can return, sure. And the only other case we have here is in just the kind of standard item. The case where there's multiple items in the list and we just need to remove the first one. So list.head equals list.head.next. And then there's the case I just mentioned where we got the potential memory leak. Is that true? I don't have to worry about its previous because its previous should be null. Now I do need to set this thing's previous. So the current list.head.previous equals null because it has no previous. It's the first item at the list. What about the node I just removed? It originally had a next. So I'll say removed or remove node equals list.head. I'll set its next equal null. Its previous should already be null. And then I'll skip it. And just to make this a little bit more readable, I'll say the list head now becomes whatever you had next. And the list.head.previous. Oh, look at that. Remove.next equals null. And then the next line I change it, so I need to do that first. List.head.previous equals null. I'm fine with that. Okay, so I think we're good there. I think that's it for the linked list. Double linked list that only removes items from the front. So let's see here. Don't have to do anything else there. Okay, we've got to add the remove head. Return the list. Okay. So I'm just going to console.log this thing and see what we get. Okay, so right off the bat we get a function for add, one for remove head, and that's it. So if I do list.add of 5, we get a head with the value 5, a tail with value 5. So add worked good in the first case. At a second I should expect to now see a head of 5 and a tail of 0. And we got head with a value of 5. Its next points to 0. Its previous is a circular reference. Cha-ching. And Then we got a 0, whose next is null. So last good. It's the tail. It's previous value next. Okay, circular reference, good. Okay, and we have the add and remove. So now let's try the remove. And the remove should now remove the first item on the list, which is 0, which should now set our head and our tail to 0. Head and tail to 0. All right. So for all the grief that circular, or not circular, that linked list gave me the other day, this one did not take so long. So good thing I had some recent experience with this. Is there anything else? Yeah, I could try seeing what happens if I remove again. I should end up with a totally empty list. Heck yeah, man, I love this. It's code's really good about how it does it. Same with the Chrome, the Chrome object. It's nice. And one thing I always forget I can do too is you can actually label the things you output. So a lot of times I used to do like kind of 2 lines, but now I can say like the list. And it will say the list, and then you can see it actually kind of puts it on the same line, so it just makes it easier to read, so you're not like 2 lines for stuff. There's a couple other nice tricks with console.log. I definitely recommend taking a look at it. You can now put like tabular stuff pretty easily. There's a couple just cool optional arguments you can do. So head is null, tail is null. That all looks good. If I do it again, it should stay null. Yep. And we'll try one more add just to see what happens. Okay, cool. So I'm going to call this sucker done. Let's take it back to leak code. So now we've got a double linked list that can remove the first item. So in here, whenever we call FirstUnique, we need to create our linked list. What's the easiest way to do this? Oh, and they do initialize, that's fine. So something like, I don't know, this dot list equals a linked list. And then I'll just loop over the nums here. We just do like const I in nums. Does that work? So not the most efficient way to kind of initialize it, but I think that's okay. Okay. So there we go. There is one other thing we need to do here. We need to keep a hash equals this. And if this dot hash already has this number, then we don't need to add it. Is that right? And whenever we add it, we save it. And didn't the hint tell us to store the node or something? Add unique numbers. When add is called, check if the number is added is unique, then have it be added to the linked list. And if it's repeated, remove it from the linked list. Use a queue and check that the first element is empty. Fine. Yeah, okay, here we go. Use the doubly linked list with a hash map of pointers to the linked list nodes. So the easiest thing here to do is just have our add actually return the node that we just added. So we can do that over here. We already have it, we just need to return it. So now if I do this, the answer should still be the same. Cool. It's a little awkward working between 2 editors. Don't love it. All right. right, so here, the hash tab, the hash item gets added just like that. And in this way, oh, but that's not quite enough. We don't just skip if the hash includes it. What else do we have to do? We have to remove it from the linked list. So, is that true? Do we have to remove it from the linked list? I don't think that we do have to remove it yet. I think we can just maybe skip it. I'm not 100% sure yet. We're going to be keeping around more numbers than we need to this way. Right now it's going to be keeping it in this linked list forever. Or not forever, but for longer than it needs to be, but whatever, we'll give it a shot. So FirstUnique will set FirstUnique equal to -1, because that's what we return if there isn't one. And then what we do is while this dot list dot head is not equal to null. So while they're, I don't want to do it that way. Let's say let current node equal the head of the list. And while we at least have a node that's not null, we will loop through and we will find a number that's unique and we'll return it or -1. And the way we know if it's unique or not is what? If this dot hash at I is the value, so current node dot is it dot value? Yep, dot value. What does that mean? It's still in the linked list. If I need to know that it's seen it more than once. So this gets the node out. But I need to know that it's different. I wonder, up here, when I create this thing, actually in here, right now I'm skipping, so I'm not recording that we've seen more than one. I'm just ignoring it. I wonder if I could say like some other value, like this dot hash and I equals, value null, some sort of like kind of like a tombstone, I've heard this called. Next, basically a kind of a dead end. So if we ever see more than one, potentially we're doing more work than we need to here. But it does make life easier down here. So we'll start with that and see how it goes. We won't be winning any awards with this one, but I never do. So if you can't win, don't try something. It's a valuable lesson for you. This dot hash dot current node dot value. So if you remember, this one will either be that kind of tombstone or it will be a valid node. So I say if the hash table at this value, if its value equals null, then you know, return -1 basically. No, not return -1. So this means it's an item that shouldn't be in our list anymore. So what we should do is say this dot list dot remove head and just get it out of here. So we never have to look at it again. Okay, I feel pretty good about that. And we'll keep it in the hash table so we know never to try it again. Because otherwise you're going to be skipping past these like tombstones over and over and over again. So else return current node dot value. Okay. And then FirstUnique prototype dot add. I think I could just steal all this behavior. Let's try this. It adds a value. So we say if the hash already has the value, then we insert the tombstone. Otherwise, we set the hash at the value equal to the node that we get. Whoa, scared me. Thank you for the follow. It's so loud when that happens. I need to get a little animation or something to play so that you can be scared with me. All right. So that's it for add. It returns void. So here then, I don't need to do this work twice. I can just say, it's going to be like this dot add. And just pass I. Okay. Doesn't return anything. This returns a number, returns in all cases. Okay, I think that's it. Finished. Got totally wrong answers. Awesome. All right, so let's take this thing over here and just comment that part out for now. And rather than just run that sample, I'm just going to try and kind of build it up from scratch and just see how it goes. So we'll say, what do they call this? First value or something. I'm just going to call it Q. We pass 2, 3, and a 4. Or 5, I think they had in their example. Now for console.log this Q, I'll give it a little note of like initial state. Okay. This dot add is not a function. Did I not do this dot new? There we go. Initial state. We have a hash table. What's this 0, 1, 2 stuff? I expected to see 2, 3, and 4. So I'm adding I instead of the value. So totally easily fixable problem. So that's probably why our answer is wrong. And this might be the only error. That would be amazing. All right, so now we got 2, 3, and 5. The tail of our list is 5. Our head equals 2. It points to an object next. Hopefully that's the 3. And that's it. So now let's see what kind of answer we got. I don't know. I'm feeling pretty good. So I probably missed something major. It's taken a while. Do I have an infinite loop somewhere? Time limit exceeded. Oh, I never changed the value of current node. Oh, geez. Current node equals current node dot next. All right. Wrong answers again. So 2, the first time we showed it, good. We added, we got null. We showed unique again, we got 2. Okay, cool. Then we added again, we got the null. And then we said show first unique, and so we got none. Am I removing the head before updating it? Probably. So we say remove head. If there's nothing to remove, then just get out of here. That should never happen. If the head equals the tail, then we null out the head, we null out the tail. It should be fine. Now remove node. We get the head of the list. We set the current head equal to this item's next. Then we null out the item we're moving's next. We set the list head, which is the current item that's now the head. We set its previous equal to null, so it doesn't reference anything. So is that what you expected to see, Trent? It's not head. We did a couple remove head tests. Cool. Oh, I appreciate it. I appreciate it. I need all the help I can get. So this looked fine to me. Yeah, let's just walk through it. So copy this over here. We'll just kind of recreate the experiment with logging. This is difficult to read. All right, so we create the thing with 235. Okay. And we said the initial state looked good. But then they went and they added, no, they did show unique, show first unique. And what does that mean? This is hard to read what they expected. So first unique, and they passed this argument. Okay. And that's it. Then they said show first unique, which should have been a 2. Okay, so here I can say something like 2 equals, question mark equals, and hopefully that's going to be a 2. It'll be show first unique. Yeah. So that's good. And then they add, I don't need to see what add does. They added a value of 5. Okay. Fine. Then they said show first unique again, should still equal 2. Okay, then they added a, I think it's the same as up here. I could have just copied this. So they add a 5, add a 2, add a 3. I hate this one so much. Alright, hopefully I muted that one. So we add a 5, and then we added a 2. And it says show first unique, and it should have been a 3 here. And then final. All right, so let's see what we got here. 2 equals 2 equals. And then, is it still running? What's going on here? That's not good. Initial state looks good. I didn't print out the state in between. Is that doing an infinite loop? Yeah, it looks like it's an infinite loop. Maybe I didn't update this code with the code I fixed that problem in. Hey, who knew working in 2 editors is error prone? Alright, yeah, the line count went up 1. So, okay. I like when the problem makes sense. And that problem, that was my bad, not the computer's bad. Alright, usually it's computer bad. Alright, so 2 expected, 2 expected. Here I didn't get the 3. And here's the state that we got. So I've got a hash where I tombstone the 2 and I tombstone the 5. Awesome. 3 does have a value at a node. It looks funky though. I expected the 3's next to be null, so that's weird. Yeah, look at this. The list says I've got a head value of 3. Awesome. But the next is fishy. Okay. And the tail is wrong. So this tail should definitely have been removed. Is that true? No, actually, I take that back. It doesn't, its next is probably fine here. Its next should point to the 5, and the 5 is the last item, because we only remove the tail if it happens to be at the first, and we notice that it's also no longer in the hash. So that's the kind of zombie problem where we've got the stuff that sticks around longer than it needs to. So this looks okay. So the problem then was the one that got first, that looked at the 3 and said, nah, that's nothing. We should skip that. So, oops. We're so close. Show FirstUnique. Shouldn't the 3 be tombstoned? So, yeah. If I did it right. Look at this though, I didn't do it right. I did, I added a 2, added a 2. And then, wait, what the heck did I do? I added a 5, and then I added a 2. So the 3 should not be tombstoned. The 2 should be tombstoned, and the 5 should be tombstoned. 3 is the only one that has not been duplicated. So I think we're good there. I think 70% sure. Show FirstUnique. So in here, we started out with -1. It said let the current node equal the head, which we saw when we debugged. That was set to 3. The current node is not equal to null. Okay. Then we took a look at the hash at 3. The value was not null, so we didn't remove it. But when we return the current node's value, somehow we got -1. So I'm just going to debug this guy. So I think that's where the problem is. 50% chance. So if we look at our queue before we began, we've got a list. It's got a tail of 5. Said that was okay. Its head is a 2. Okay. We haven't removed anything. We just added the 2, so we don't even know that it's bad. Okay, but if we look at our hash here, we should see the 2 is tombstoned. So let's double check that in the hash. The 2 has been tombstoned. Then 3 is the only one that's good. Okay, and if we look at its value, it's got a value of 3 too, so that looks like I expect. All right, so if we step into here, F11, our list head is 2. Okay, so we come in, it's not null, so its value should be null, but it's not letting me mouse over it for some reason. But I should be able to see it's 2, its value. What? No. That's okay. I'm looking at the hash at 2. Its value is null. So we should remove the head at that point. And I believe this operation happens correctly. So then what happens? We're going to set it equal to the current node's next, which is null. And I think this is basically, you called it, Trent. You called it. So yeah, I looked only at this function when you mentioned that. And I didn't think about anything else that was like messing around with that. So yeah, this item has been altered. So we remove the head. So I almost want to say like, let's want to set it ahead of time. So it becomes this dot list dot head. It's the first item. Dot next. Apparently I could just return that when we remove it, but I don't know, that's kind of weird. Oh, you know, another way to say that is just to say that current node equals whatever the head is. Nope, can't do that. Yeah, this is a weird condition where, yeah, I'm not like iterating through normally. So I can go ahead and store a pointer to the next item. Let's see how this looks. I think this is it. I've said that a few times tonight though, as is usual. Okay. Let's make some room here. Initial state, 2 equals 2, 2 equals 2, 3 equals 3. When we look at our final state, we've got 3 here. It's the only value that is good. Then we've got a 5, so looking good. Just double check it here. I don't think there are any special cases we need to watch out for. I think it's just gonna work. Fingers crossed. Yeah. 28 is in the bag. All right, and Trent, you totally called it. The problem was because I was altering arguments. It's mutability strikes again. So Trent called it. All right, there you go, immortalized. Your name is in the database. How do you think they store your solutions? Because you can retrieve them at any time. Is it a relational database or do they just write it to disk? I don't know. I kind of feel like I would just stash it in S3 because I'm lazy. I don't know, maybe Mongo. All right, let's see how it performed. Not enough submissions. No. All right, well, I'm going to assume it was perfect. 100%. All right, cool. So awesome. We got 2 more days. And this will be the first time I completed a contest, and it was a doozy. There were some really tough ones. This one's kind of weird. They definitely threw us a bone by literally telling us how to do it with the first hint, not even the third one. We could do better by making a heap. I still don't understand. I mean, I guess I understand how worst case scenario we have to go through every item in the linked list and remove it. In the case they like added a whole bunch of duplicates, then we'd have a lot of work to do when we say find FirstUnique. So I don't know. I don't get this. Okay, what if the heap was a min heap and the value that we sorted by, we store the nodes in there, but the value we sort by is its frequency. So every time we see one, we, increment it. And then that way the ones would always sort to the top, but you would just have to make sure to, I don't understand this. I don't understand the heap. Make a binary tree and just push all of the duplicated values behind it. Yeah, I kind of think that's what they're getting at here a little bit. I'm having a hard time like really understanding what that means. So I've got a tree. Heap is a binary tree. It's perfectly balanced. Well, that's not true. It's not perfectly balanced. It gets filled in left to right. So I don't know. Oh, maybe we can view the discussion. Go to discuss. First unique number. I want to see one with the heap. All right. So they got a doubly linked list, a hash map, heap mover. So whenever they delete the node, see, my understanding of a heap is that it's like you're guaranteed to always have the minimum or maximum item at the top, but you aren't always guaranteed to have the rest of the heap in any guaranteed order. Now, when you pluck the first item off the top of the heap, then you have a log_n operation to get the next smallest number up to the top of the heap so you can pluck it again. So it's always fast to remove the minimum number. So how does this help with it? What I don't understand is like when we pluck the top of the heap off, how do we know whether to go with the left child or the right child? Like it kind of makes sense almost to always sort them left or right in the order that you saw them. But the problem with that is that kind of goes against the nature of the heap. Like you're supposed to always fill in left to right. Oh, and maybe that's okay. Maybe that's okay. So if both numbers are 1, then just always take the left one because you know that you saw it before. That's the secret. The deal with a heap is you fill it in left to right, which is the order that you get the items. So then whenever there's a conflict, like you pluck the item off the list, which would happen when you see a duplicate of it. Okay, that's really slick. So basically the deal is every time you add a new number, you check if it's the top of the heap. If it is, then you take it off and re-add it to the bottom, and then you'll have to shuffle the tree in order to get the next value, the leftmost value that has a frequency of 1. Pop it to the top, rejigger the rest of the tree. And just like you said, Trent, you called it again. You essentially got a binary tree at that point with all the duplicated values at the bottom, so you never have to go that deep. In fact, you never have to go past the first node. The only thing is when you do that shuffle, longer insert time. So basically you're doing a log of insert, worst case scenario, which is when you have duplicate value. But even then, it's really not too bad because you only have to fix the tree. You take that top item off, put it at the bottom, and then percolate up. But in this particular case, we know that the percolate doesn't really have a lot of work to do because it's only 1s and 2s that matter. Like you don't even care about 3 or 4, the rest of the frequency. It's enough to just say it's 2. So when you percolate up or percolate down, I forget which one goes, which one's which, then you shouldn't have that many shuffles to make in order to get it right. Basically, you'll move the 1 up to the top position, and then you'll move either a 1 or 2 in to fill it. And if it's 2 that you move up, then the next values that you kind of compare at are going to be equal, so you don't have to do that many swaps. So it's like the best case scenario for a heap, really. Okay, so that makes sense. So it's a better way of keeping the minimum items up front, because in my double link list, the worst case scenario is that we have to go through the entire list to find that none of them are unique. So I would end up removing. Remove is fast from linked lists. It's only operation 1, but because we have to go through all the items that we've seen so far, potentially is N. So this has a better runtime, but it's a lot more coding. So yeah, can I like it or something? I don't know. I'm tempted to say very nice, but I don't actually know if it works. Oh, I can vote it up though. There we go. All right, cool. Well, that's it for me tonight. I'm going to go play video games now. Borderlands 3 is calling my name. So you guys have a good one, and thank you very much, Trent. Really appreciate the help there. We got 2 days left. Woo. Sayonara.